Okay, here's section 8.7, and we're defining a plane, and we'll also do the first theorem, theorem 8.7.1. And so their definition for a plane is a set of points P, okay, excuse me, a set of points P such that, and so we're using vectors and points kind of, that we go back and forth with these things. And they just write, they write it this way: P equals P0. So any associated vector P with the point is some initial vector P0 plus S times X plus T times Y, where S and T are elements of the real numbers. And so they're just, what this is saying is a plane is a two-dimensional space here, because I'm making it with these two vectors. It's a two-dimensional subset of, say, 3 space or 4 space or 5 space or whatever. But so here I've got this two-dimensional subspace of R3 with, using X and Y, and well, subspace. Ooh, I got to be careful there. Yeah, if P0 were the origin, I guess it would be a subspace. Anyway, I digress. So we have P equals this P0 plus S times X plus T times Y. So, such that, for any, and this is where it's a little tough, because a set of points P. So I think they mean the set's not named P, it's the point that is P. So for P element of our set, and I'll try to use some sort of different notation for our set, for our plane. So this P here is our plane. These are the set of points that are in the plane, and they satisfy this vector equation if we think of them as their vector. Okay, so as parameterized things, we would have like an X equals some X0 plus X A1 plus TA2, and Y with some Y0 plus S B1 plus TB2, and Z is Z0 plus S C1 plus TC2. So there we could write a plane in a parametric form with 2 parameters, S and T. Okay, and they point out that these are all non-zero. So our P0, X, Y are non-zero and non-parallel or non-proportional. Okay, so that's our definition of a plane. So anything we write like that, we can call it a plane. Now, that gets us quickly to theorem 8.7.1. And this is our 3 points determine a plane theorem. So they say let A, B, C be 3 non-collinear points. Then there is one and only one plane containing or through containing these points. And we can get that simply by using direction vectors. Now, you know, we could do this with any of the A, B, or C because we could always rename the points. And so that's just something to realize. And so we can write this as the vector P is A plus S times the directed line segment from A to B, or that vector, plus T times the vector from the directed line segment of AC. Okay, but again, we could swap out the A with the B or the A with the C and write it accordingly that way. And they say, or equivalently, we could do it as AP equals S times AB plus TA. Okay, so now the equivalent part here is AP here is just P minus A. Okay, so all they did was they subtracted A from both sides. Okay, so nothing startling there in that. Now, so for a proof here, we've got two things. We've got existence and uniqueness. Okay, now the existence part is pretty simple. Right, for the existence part, notice that, let's see, we'll let S equals 0, T equals 0. So in our proof, you know, first we're looking at existence. And if we have S equals 0, T equals 0, then what we get is our P is equal to A. Oh, yeah, true. Right, so that takes care of A. Now, if we let S equal 1 and T equal 0, then what we have according to this is P equals A plus AB. Okay, now so remember that's the directed line segment from A to B, right? Or if we think of it as vectors, the vector idea, AB is B minus A, so this is A plus B minus A. Oh, but that's B. And so we've got the point B in there. And then S equals 0, T equals 1. We have P equals A plus our directed line segment AC. But again, that is A plus C minus A. And so there's our C. So there we have existence. Okay, now what we need is uniqueness. And so typically for uniqueness, one way to go is just assume there's another plane. So our original plane, we're gonna call this, plane up here P, and assume a Q plane, P equal some P0 plus Sx plus Ty. Okay, and it contains the points A, B, and C. Well, then, if that's the case, I could write A as P0 plus some S0x plus some T0y. Okay, because Q has to contain A. Right, so if that's the case, we can also write P equals A plus S minus S0 times X plus T minus T0 times Y. Okay, so what the heck happened there? We just subtracted the point A, or the vector A, from this thing. Okay, we took we took this whole thing and we subtracted A off of there. Okay, and so this is A plus some S prime X plus some T prime Y, different letters for those differences there. And then what they're saying is, well, then, in essence, use A for P0. Okay, and they similarly they do the same thing with B and C, and they write that, well, B is some A plus S1x plus S2y, and C equals A plus T1y, and then S2x plus T2y. Okay, and because they're both in the plane, and so what they're pointing out is that well, so A, B, and C are all in there, and they're in P, and anything we could write from P, we could write this way. So they're saying that, well, let me write that P the right way. They're saying, hey, that gives us that P is a subset of Q. Then, conversely, they say it's straightforward to show that A, B, and AC are not parallel, and they can get any vector in Q to be written as a vector in P. Now, I'm not going to go through the rest of that with this, but just to point out that, see, this was the idea back here, is they wanted to show that anything in P So back here, P, okay, P looks like that, okay, where we need linear combinations of A and C, right? Well, so they did a transformation, but you see we have these X's and Y's. But now they're going way back to our stuff with bases and independent vectors and dimension and all that kind of stuff, and saying, look, okay, I can write A as some, you know, A can be written as something in Q, right? And then, in particular, I can write any vector in Q, or, sorry, I can write any vector this way if I want. Yeah, in Q. And then, so I write B and C this way. Okay, now what they've kind of glossed over is tying back to those theorems, you see, is that just having B and C don't necessarily tell me that all of P can be written using these basis vectors of X and Y. But what I can do then is, since B and C are linear combinations of A, X, and Y, then all linear combinations of A, B, and C, okay, so any linear combination of A, B, and C can be written as a linear combination of the A, X, and Y. And so by doing that, that says that P is in Q. So we have to go back to that stuff, that, you know, linear combinations of linear combinations, right? The stuff we did back in, I don't know what chapter that was, chapter 3 maybe. We're using that here to say P is a subset of Q. And then similarly, you know, they need to show Q is a subset of P. And then once they get that, oops, P like that, then once they get that, if they're both subsets of each other, then P is the same as Q. It's the same set of points. Because remember that the way they've defined a plane is by a set of points that satisfy a particular equation or set of equations, depending on how you look at it. And so it's a set of points. So to show that one set is equal to another, typically we show first that one set is a subset of the other, and then reverse it. And so that is what their proof is doing to get the uniqueness, that if we assumed we had a second one, well, it was just equal to the first one. And we'll stop there.